Hey class, so here's another example problem for you. You've been called in by some aerospace engineers, I guess, because of your superior knowledge of physics, to help them out. They're designing an airplane, and you need to help them size the propeller on the front of this airplane. So they tell you a few things. They tell you, first of all, that the propeller is going to be spinning or rotating at 1,500 revolutions per minute. And you're also told that this plane needs to be able to reach a maximum speed of 90 meters per second in the forward direction. And because of the material, you are also told that the total overall speed of the tip of the propeller cannot exceed 300 meters per second. So first of all, you might think, well, if you're only moving at 90 meters per second, then you're going to be well under 300 and you're good. But we're looking at the overall total speed. So that means that the propeller, which is going to be moving forward at 90 meters per second, but also rotating, can't exceed that 300 meters per second. And so you're asked to help the engineers by determining what is the maximum possible radius of your propeller in order to stay under these limits, but still maximize the overall size to try to maximize the lift force to propel yourself forward. So go ahead and maybe pause this one. Try to see if you can figure it out. It's a little bit of a tricky one for sure, so take a minute, try to work on it. I'm going to go ahead and progress. So you can see here in the picture, you can think of the airplane as really having two perpendicular directions of motion, or really the propeller, not the airplane, the propeller. It's going to have its forward velocity of 90 meters per second, but it's also going to have a tangential velocity perpendicular to that forward direction of motion. So for example, if we were to turn the airplane sideways and look at the tip, so here's the tip of the propeller, maybe here's the rest of the airplane. Okay, this is not a very good picture, but you get the idea. Here's an airplane that, I don't know, looks like a weird animal. Okay, so anyway, if this is the tip of the propeller as it's going past you, moving in the downward direction, you still have the velocity of the plane forward, and you have the velocity, the tangential velocity of the tip in the downward direction, right? And if you froze it and looked at it from the other side, then the tangential velocity would be up. If you froze it when it's up here at the top, then the tangential velocity would be to the left, and so on, right? It just depends on where it's at, what direction that tangential velocity is. But the overall net velocity, as you can kind of visualize from this picture here, the overall net velocity is going to be off like here. So the V total is going to be off in this direction. And so the magnitude of your total velocity, which that's what can't exceed 300 meters per second, the magnitude of your net velocity is just going to be equal to the square root of the sum of the squares of its individual components. So the square root of the forward velocity of the plane squared plus the tangential velocity squared. All right, so let's think about what we know and what we don't know in this setup that we have here, okay? So we know that the total velocity of the plane, its magnitude, cannot exceed 300 meters per second. We also know that the velocity of the plane itself in the forward direction is going to be 90 meters per second. And the tangential velocity, we do not know, but we do know, as you can see here, and as we've learned, tangential velocity is equal to omega multiplied by r. So, with that in mind, we should be able to substitute all these numbers into our equation up there and solve for r, except what is omega? Well, we're told right here, boom, omega is 1,500 revolutions per minute, but we need radians per second in order to continue. So omega, which is 1,500 revolutions per 1 minute, we can do a unit conversion to convert this into radians per second in order to get the appropriate units. So we can go ahead and we know that 1 revolution is 2 pi radians, and we know that 1 minute is 60 seconds. And so if you do that conversion, it should come out to be 157 radians per second. Now let's go up here and work on solving this equation here. I'm going to replace magnitude of the vector v total. I'm just going to rewrite that as just v total without the vector sign, because that's how we represent magnitude. So if we work on this problem here, continuing on, we have, whoa, okay, wrong button. Sorry about that. Let's try this again. Okay, so we got V total. I'm going to square both sides. So V total squared equals the velocity of the plane squared plus now V tangent is omega times r, quantity squared. So I want to get the r by itself. So I can have omega squared r squared equals, I still have V total squared, and then I'm going to subtract the V of the plane squared to the opposite side. And now I can divide by the omega squared and take the square root. So r equals the square root of the total velocity squared minus the velocity of the plane squared over the angular velocity of the propeller, quantity squared. So we plug in our numbers here. So we got the square root of 300 meters per second squared minus 90 meters per second squared, and all divided by 157 radians per second, once again squared, lots of squareds and square roots. But you plug and chug, and guess what? You calculate that the propeller must be less than 1.82 meters long. Now, in reality, you're probably going to make it even smaller than that to be safe, kind of to account for a safety factor, but you've now given them a value with which to work that fits exactly into the parameters given to you. So again, tricky one, not a lot of different equations, really just understanding translational and rotational motion and how they relate to one another. So I hope that helps, and I hope you have a great day.